Hello and welcome to one and all present here. So this is week 11 of the problem solving session for the course of Introduction to Fluid Mechanics. So myself Kalpita Nath, and I'm research scholar at IIT Kharagpur. So let's wait for 5 minutes for others to join, and then we'll proceed with today's session. So I think we should start. Uh, okay. So first of all, we start with the derivation of the Navier-Stokes equation. So how all of this started? First of all, this is a study of dynamics of viscous flows. Till now, we have ignored the viscous term. Now we will consider it. So that will constitute in the Navier-Stokes equation. So first of all, let us take a fluid element. So let's suppose this is a fluid element. So this is one surface, this is another surface. Let's suppose this is X, this is Z, and this is Y. X phase we can also represent as X1, Y can be represented as X2, and Z can be represented as X3. Now, let us understand how we will take the normal stresses and the shear stresses. How we will represent? We will represent this as tau ij. So this is the I is the direction normal to the face. Like where is the direction of the normal when we are considering, like let's suppose this is the face. So when we are considering normal to, like normal to this face, then this is the normal to this face, right? So when so this is the direction of the normal to the face, that is in x1 direction. So this is direction of normal to the face, and this is direction of force. Okay, so let's suppose, let me delete this. So if I will represent this, what will be the shear stress? Can you tell me on this direction? See, this is the first we need to understand what is the normal direction. The normal direction for this force is in 1 only, and the force is also in 1. So this is tau 1 1. Similarly, if we will write for this direction, so this will be tau. The normal for this surface is 1, but now the direction of force has changed to 2, is it not? Similarly, if we write in this phase, this will be tau 1 3. Just the opposite phase, if we will write, see, this is in negative tau direction, sorry, negative 1 direction, right? Still we are represented, there is no representation of negative sign here, we will represent just the direction. This will be along -1 direction. Now, as this is tau 1 2, if we will represent in this direction, this will be like tau 1 2 will be in this direction. Why? Because this is in negative y direction. So to compensate for negative y direction, we can't give minus. So that's why we are just showing this in the negative y direction. Right. Now for this is tau 1 3. So we are drawing this along minus x2 and the normal along minus x1. Now this is a this is what? This is not a vector, right? This is a second order tensor when a vector is mapped on a vector. So like if we will go for further considerations, we will consider surface forces and body forces. So these surface forces are those forces that are expressed as tau ij. This will represent the normal force and the shear force. Normal force is when I is equal to j, and shear force is in when I is not equal to j. Right. Now forces acting on the fluid element along x1, like if we will represent that. Now we have just represented the direction of stresses. Now we will represent the forces. This is the fluid element. This is tau 1 1. Now let's suppose this is del x2, this is del x3, and this is del x1. So now if you want to represent tau 1 1, this will be like, first we will represent on this side. This will be tau 1 1. This face is the area of the shear stress. Stress is pressure into area. So area will be delta x2 delta x3. So this will give the force. Now from this force we have taken this. There will be a, like if we want to represent on this face, that will be delta x1 change over there. So this will be tau 1 1 plus delta 1 1 upon del x1 delta x1 plus some higher order terms multiplied by delta x2 delta x3. Similarly, if you want to represent for y direction, so this will be tau 2 1 del x1 del x3. Similarly, this will be in just in equal and opposite direction, tau 2 1, but it will change del x2. So del tau 2 1 del x2 del x2 plus higher order terms multiplied by del x1 del x3. Okay, now if you want to represent the z direction forces, let me say take some other color. So this will be, let's suppose on this phase. First we want to represent on this phase, this outer phase. So if we want to represent on this phase, this will be tau 3 1 del x1 del x2. Right. Now for this phase it will be tau 3 1 plus del tau 3 1 del x3 plus higher order terms multiplied by the area del x1 del x2. Okay, now these are the surface forces. Let's say b1 is the body force per unit mass along x1. So the resultant of all forces along x1 will be del tau 1 1 del x1 del x2 del x3 del x1. Cause this like if we take for this and this will get cancelled, right? So only this will keep, but this will stay. Del tau similarly for other phases also, del x2 del x1 del x2 del x3 plus del tau 3 1 del x3 del x1 del x2 del x3. Then the body force term, this will be the per unit mass, so we'll multiply by mass. Mass is rho into volume del x2 del x3 plus some higher order terms. Now this we will take together. So this will tau 1 1 by tau x1 plus tau 2 2 2 1 del x2 plus del tau 3 1 del x3 del x1 del x2 del x3 plus higher order terms. So this will be summation j is equal to 1 2 3 del tau j I, sorry, j1, this suffix is 1, so del xj plus rho b1 del x1 plus, sorry, del x2 del x3 plus dot. That means the higher order terms again. So this we can represent as, like, if we represent for as general term, so let's suppose fxi, like for any direction x y, sorry, 1 2 or 3. So this can be represented as summations j is equal to 1 2 3 del tau j I by del xj plus rho bi del x1 del x2 del x3 plus higher order terms. Now, by Einstein, like, what he said that if there is a repeated index, like this j is equal to 1, this j, and this, there is a repeated index, right? So we can simply omit, or this summation becomes invisible. So this will be del tau ij del xj plus rho bi del x1 del x2 del x3 order terms. So summation is there, but we are not like showing this. Now, according to Newton's second law, this is equal to delta mass into acceleration. Is it not? So I'll give you 1 minute. Can you write this del m into acceleration? What will be the value, like formula for this? Please write this down. Okay, so let's write this down. So mass, obviously mass we will write as rho del x1 del x2 del x3, and this acceleration we can write, we have already written this as complete acceleration del t plus u1 del ui del x1 plus u2 del ui del x2 plus u3 del ui del x3. This is equal to this whole term, right? Will be coming here. Right. Now, this can be represented how? This can be represented as like, it can be represented as uj del ui del x. Because of repeated index, we can omit the summation sign. So del ui del t. This I am saying this can be represented as this. So del ui del t rho del x1 del x2 del x3. Now, as per sign convention, acceleration should always be written on the right. So acceleration is equal to all the forces. So what are the forces? Del tau ij upon del xj plus rho bi del x1, del x2, del x3 plus higher order terms. We need to write the differential equation at a point so that we can take limit 0. Now we will take limit, like for a point we want to find out, right? So for a point if I want to find out, we will take del x1, del x2, del x3 tends to 0 and limit of that. Center volume is shrinking to just a single point. If it happens so, then all the higher order terms will tend to 0. So the whole equation will become del ui del, this is the acceleration part, uj del ui del xj is equal to del tau ij del xj plus rho bi. This is Cauchy or Navier equation. Now, what are the unknowns here? Here rho is an unknown, u1, u2, u3, tau, ji, all of these are unknowns. Tau ji itself is 9 components. So total how many? 13 components are there. Now, how many equations do we have? One, we have continuity equation. Another we have, another three we have rather. So that is x momentum equation, y momentum equation, and z momentum equation. That means x1 momentum equation, x2 momentum equation, x3 momentum equation. So there are 4 equations and 13 variables. So that is not solvable. So we need to reduce the number of variables. How to do that? Can you tell me? Okay, let's just tell me like what next we should do, how we should proceed forward to reduce the number of variables. I'll give you 1 minute to answer this. Okay, uh, so what will we do now? We have taken everything on linear momentum consideration. We have not even taken the angular momentum part. So now we will do angular momentum consideration, that means the rotation. And what is linear momentum? That is a translation. So we will take angular momentum consideration. Angular momentum consideration. So for that, so first of all, let's suppose rotation is taking place with respect to z axis, that means x3 axis. So we will consider the forces which are there in xy plane. So let's suppose this is the rotation is taking place in this point, like this is the axis of rotation. Let's suppose there is a force in, this is x1, right? this is x1, and there is a force in this direction as well. Let's suppose the normal forces first we are considering. So we are considering force in this direction. This will be tau 1 1, like if this direction is tau 1 1 delta x2, this is delta x2, and this is delta x1 delta x2. So this is tau 1 1 plus del tau 1 1 del x1 delta x1 delta x2 1. So now if we will go for other surfaces, let us go for the translational motion. So in this direction there will be one translational motion. So this is tau 2 2, like if we get the normal forces here, this is tau 2 2 delta x1, and this is tau 2 2 plus del tau 2 2 delta x2 delta x2 upon delta x1. And in this direction also there will be one shear force, so this will be shear stress or force rather. Sorry, this is tau 2 1 del tau 2 1 del x2 delta x1. Why we are taking 1? Because 1 is the width in the z direction. We are assuming that. Now we need to find out the shear forces on this direction as well. Let me use some other color. So first it will be on this direction. So and first it will be on this direction. This direction it will be tau 1 2 delta x2, and this is tau 1 2 plus tau 1 2 del tau 1 2 del x1 delta x1, and this is delta x2. Okay. So tau 1 1 and tau 2 2, as I said, is the normal forces, and tau 1 2 and tau 2 1 are the tangential forces. So we are interested to find the moment of the forces. So in that del 2 1 del x2 del 1 2 del x1 del 2 2 del x2 and del 1 1 del x1, the incremental changes does not matter. So tau 2 1, that is the top and bottom, are equal and opposite and are anti-parallel. So they will form a couple clockwise. Tau 2 1 and this top and bottom, tau 2 1, that and this, they'll clockwise movement, and tau 1 2 will form a anti-clockwise movement. You tell me this one, right? Anti-clockwise movement. Let me use some other color. This is anti-clockwise movement in this direction, and for this, if we'll use some other color, this, let's suppose we are taking this color. Okay, so for top and bottom, in which direction it is? This is in this direction, this is in this direction, so this is in clockwise direction, right? The rotation, we are considering that only. So tau 1 2 delta x2 is tau 1 2 delta x2 is the force, and delta x1 is the arm of the moment. So if you consider that, that will be tau 1 2 delta x1 delta x2 minus tau 2 1 delta x1 delta x2 plus higher order terms is equal to the moment of inertia, multiplied by the moment of inertia multiplied by angular acceleration. Is it not? So this is the sum of all moment about that point O, and that is equal to moment of inertia multiplied by angular acceleration. Moment of inertia in that axis only. So we can write this. There is a formula 1 upon 2L density into mass del x1 del x2 multiplied by one arm square plus other arm square multiplied by theta dot. That is the angular acceleration. Now we will take limit del x1 del x2 tends to 0. So if we will take then that all of this will be 0. So this will be tau 1 2 is equal to tau 2 1. That means tau ij is equal to tau ji. So from this consideration, what we get is that among the 13 unknowns, 9 tau ij's are there and only 6 are independent. So this 13 now reduces to 10. 10 unknowns. Now still we have a lot to go. So we need additional constraints to solve. So we look for additional constraints that will come from the constitutive behavior of the fluid. Like for fluid, stress is equal to function of rate of strain upon deformation. So rate of deformation is del ui del xj is equal to half del ui del xj plus del uj del xi. So plus half this we already have started in fluid kinematics. So this is del ui del xj minus del uj del xi. The first one is the rate of deformation, second one is the rotation. So the rotation will contribute to the stress, deformation that will give rise to stress. Now when fluid is rest, the stress is due to pressure, the normal stress. When the fluid is deforming, the stress is due to pressure plus the stress is due to deformation. So when it is linear, that is what there is volumetric deformation, and when it is angular, there is shear deformation. Right. Now for volumetric deformation, the expression is given by del dot v vector is equal to del u del x plus del v del y plus del w del x. And for shear deformation, the expression is del ui del xj plus del uj del xi. If I and j are same, it represents linear deformation. That means this can be represented del u1 del x1, del v1 del x, del u2 del x2 and del u3 del x3. So this can represent del uk del x. Okay. Right. So tau ij is a function of pressure del uk del xk and this one del ui del xj plus del uj del xi. Now to isolate the normal and shear component, we use the Kronecker delta, delta ij. Delta ij is 1 when I is equal to j and is 0 when I is not equal to j. Right. So tau ij is a function of pressure del u del k. So tau ij can be represented as function of pressure del uk del xk delta ij, the Kronecker delta. These are the normal components plus function of del ui del xj plus del uj del xi. For Newtonian fluid, the relationship between tau ij and the rate of deformation is linear. If the fluid is homogeneous and isotropic, homogeneous means position dependent and isotropic means direction invariant. That can be represented as by the position independent and direction invariant fluid property called viscosity. So tau ij in total we can write as P delta ij plus lambda del uk del xk delta Kronecker delta delta ij mu del ui del xj plus del uj del xi. Now this is a positive, this is positive sense, this pressure, like why negative here? This is the pressure is positive sense, so the pressure is compressive in nature. But this tau ij is positive sense of normal, so it is tensile in nature. So in order to like compensate for this, we gave this negative sign. This is volumetric dilation coefficient, this one, and this mu is viscosity. So this is the generalized form of Newton's law of viscosity. Now what we use mu du dy, this comes from this only. So what happens is that tau xy viscous is equal to mu du dy plus dv dx. So if the flow is unidirectional, tau is equal to mu du dy, which we use. That is a special case actually, right? Now if we will write for 1, 2 and 3, this will be tau 1 is equal to minus p plus delta del u k del x k plus 2 mu del u1 del x1. Tau 2 is equal to minus p plus lambda del u k del x k plus 2 mu del u2 del x2. Now tau 3 is equal to minus p plus lambda del u k del x k plus 2 mu del u3 del x3. Now here this p is the thermodynamic pressure. If we will add those all of these 3 and divide by 3 to find the mechanical pressure, this p is thermodynamic pressure, as the pressure will be related to thermodynamic equation of state. For example, in case of like if idle gas is there, p is equal to rho RT. So this is the thermodynamic pressure, this p. Now what is mechanical pressure? If we will add this 3 up and divide by 3, this will give the mechanical pressure. The mechanical pressure is minus tau 1 plus tau 2 plus tau 3 all the normal components upon 3 normal shear stresses. So this Pm, like from this equation, if we will get what? Minus P plus lambda plus 2 mu by 3 del UK del xk. This explanation that related mechanical pressure to thermodynamic pressure. Now cases when mechanical pressure is equal to thermodynamic pressure when Pm is equal to P. Now first when these two pressures will be equal, when this will be 0, first case. When the fluid is dilute and monoatomic gas, we have only translational degree of freedom and no other degrees of freedom. Cause why? Like what happens is that this mechanical pressure reflects the translation degree of freedom of molecules, and this thermodynamic reflects all sorts of degrees of freedom like translation, rotational, vibrational, etc. So if the translation degrees of freedom is only there and no other degrees of freedom is there, then obviously this whole term will be 0 and Pm is equal to P. Now another thing is that Stokes hypothesis. That is lambda plus 2 mu by k is equal to 0. Then Pm is equal to P. The fluid that obeys this relationship is called Stokesian fluid. So for that, lambda is equal to minus 2 by 3 mu. Now that if we let me introduce some definitions. That is, if the time taken by a fluid to adapt to changes imposed in it is called the relaxation time. If a fluid cannot convert all the degrees of freedom to the translational degrees of freedom instantaneously for a very rapid change, when time scale of imposition is faster than the relaxation time, then Stokes hypothesis will no more be valid. On the Stokes hypothesis is only valid when the time scale of imposition of disturbance is significantly larger than the relaxation time. So the fluid relaxes almost instantaneously. So there is that attains equilibration of mechanical and thermodynamic properties. So this happens only in this case, like, and that is mostly in in most situations this will valid only. So let's say the Stokes hypothesis is valid, then lambda is equal to minus 2 by 3 mu. So tau ij for Newtonian homogeneous isotropic instruction fluid minus p delta ij plus minus 2 by 3 mu del uk del xk delta ij mu plus mu del ui del xj plus del uj del xi. Now Navier's equation. Navier's equation is rho del ui del t plus uj del ui del xj is equal to del tau ij del xj plus rho bi. From angular momentum consideration, tau ij is equal to tau ji. We already got that. So but this is only valid in the absence of body couples. Remember that. So this can be written as rho del ui del t plus uj del ui del xj is equal to del tau ij del xj plus rho bi. Now Stokes hypothesis lambda minus 2 by 3 mu. If we put this in the main equation, so we know that delta ij is equal to 1, so I is equal to j. We will put in this pressure term. So this will be rho del ui del t plus uj del ui del xj del p minus del p del xi plus del xi lambda del uk del xk plus del xj mu del ui del xj plus del xj mu del uj del xi plus rho bi. Mu is equal to constant, and del xj, like this term, let me use some other color. This term, this can be written as like index can be written as del del xj del xi. Mu can be taken outside, del xi del uj del xj. So it can be written as in terms of k. So it can be written as del x, and mu can be taken inside again. So if we will do that, del xj mu del uk del xk. So sorry, this is I. Because whether you write j or k, that doesn't really matter. So this whole thing will become minus del p del xi plus del xj del xj mu del ui del xj plus del xi, this whole lambda plus mu, we can write del uk del xk plus rho bi, the body force term, right? So if the fluid is Stokesian fluid, then this can be like lambda is equal to minus 2 by 3 mu. So this whole term can be written as mu by 3. So this is called the momentum conservation equation and Navier-Stokes equation, and assumptions used here are homogeneous, isotropic, Newtonian, Stokesian fluid and no body couple. Now, if we will write continuity equation, so del rho del t plus del xj rho uj is equal to 0. Now the number of independent equations are continuity and 3x momentum equations, and number of unknowns are rho, u1, u2, u3 and p, pressure. Now how they will close, how we can close both of them. So rho is known, like let's suppose density is known given, then there are 4 equations and 4 unknowns we have, so it can be solved. If rho is not given, we need rho in terms of pressure and temperature. Then another variable comes, that is temperature. So where like in order to solve for temperature, we'll use what? We'll use the energy equation. So this is all about Navier-Stokes equation, and if we do not want to use any assumptions, then we need to, like, over here, if we don't want to use this, so we can go for computational dynamics. So that can be used for solving this kind of partial differential equation, right? This whole equation to solve this. Let's now move to the questions. Okay, let me move to the first question. So consider the following statements. The hydrostatic component of stress on a fluid element is independent of deformation in the fluid element. The deviatory component of stress on a fluid element is independent of deformation in the fluid element. The mechanical pressure represents the effects of translational motion of energy of the system of molecules. And the mechanical pressure represents the combined effect of translational, rotational, and vibrational modes of energy of the system of molecules. Which of the above statements is or are true? Tell me that. So I'll give you 1 minute to solve this. Like, you have to give some concepts. Do that. Uh, okay, so So obviously the answer will be which one? The first obviously first one is correct, and the second one is not. And the third one, the mechanical pressure represents the effects of translational mode of energy of the system of molecules. So that is also correct. And the fourth one is again not. So that means option A. Okay. Let's proceed to the next question. Which of the following correctly defines the relationship between mechanical pressure and the stress tensor component in a fluid element? So, obviously, we have just learned about it, so this will be option A. This negative sign represents the like pressure is in the opposite direction to the normal stress tensors, right? So that's why this negative sign. This one. So, which of the following is not correct about Navier-Stokes equation? Now, Navier-Stokes equation is valid for both the compressible and incompressible flows. So, the first one is obviously wrong. And next is the there is set of coupled second order non linear partial differential equation, but that is right, no? So that is, which one is not correct? So uncoupled second order, so this will be 1 and 3, that means option B. Okay, so what about this? A crankshaft journal bearing in an automobile engine is lubricated by an oil at 100 degrees Celsius. The bearing diameter is 7.5 centimeter, and the diametral clearance is 0.00635 centimeter, and the shaft rotates at 3602 rpm, and it is 3.175 centimeter long. The bearing is under no load, so the clearance is symmetrical. Determine the torque required to turn the journal. Okay, so given the viscosity of the oil is given, so what will be the torque? So you solve this. I'll give you 2 minutes to solve this. Then we'll proceed with the solution. Okay, let me give you a brief idea of what is happening here. So there is a shaft. So there is a shaft, right? And the velocity profile that is taking place here. So there is a velocity profile. Like if we will see here, so this is the bearing, and this is the shaft, the outer portion. The liquid is inside. So there will be some velocity profile that will be formed here. Right. So if we will do the free body diagram, this is the bearing. This is the weight force. Weight force we are neglecting here. This is the distance between that is r, and this is the like here, if we will represent here, this is the friction force. This is the friction force due to friction. So that can be represented as mu w, sorry, mu omega. And okay, so now solve this. We'll proceed after 2 minutes. Okay. So first of all, the torque on the journal is caused by the viscous shear on the oil, right? And the gap in width is small, so the flow may be modeled as a flow between two infinite parallel plates. Now, let us take assumptions like the flow is steady, laminar, and incompressible. So the shear stress can be written as mu velocity by A. This is the velocity of the top plate, and this is the gap between the plates. So tau can be visible, right? Yeah. So tau can be written as mu u by A. So that is u is equal to the velocity. The linear velocity is equal to angular velocity multiplied by the, like, this is whole d, and the point of action, right? The point of action is d by 2. So mu omega d by 2 A. A. This A. Now, this omega, how can we write in terms of the rotations rpm is given? So how it is related? Omega is equal to 2 pi this rotations upon 60. So in place of omega we can write mu 2 pi n d by 2a. So this will be 0.0096 multiplied by 2 pi into 60, 0.075. How come 60? Because this is 3600, right? So that's why. So 100 upon 2 multiplied by 0.003175. So this will be given as 427, 4.4188 Pascal. Now the torque, how can we write the torque? So let's take the formula for this first. So the friction force can be written as tau multiplied by area. Force, stress multiplied by area, simple. So the torque is given as the friction force multiplied by the radius of action. So radius where like from which direction the torque is taking place, from the axis. So this will be, the friction force is tau AR. So this is tau into 2 pi R L into R. So this will come out to be 4274. Tau is already, we know, 4188. 2 pi 0.075 by 2 whole square, 0.003175. So this will come out to be 0.1199 Newton meter. Done. Okay, so let's proceed to the next question now. So a flow of oil is there with density and viscosity of the oil is given in a 28 centimeter diameter pipeline at an average velocity is also given. The length of the pipeline is given. Disregarding the entrance effect, determine the pumping power required to overcome the pressure losses to maintain the flow of the oil. So disregarding the entrance effect, so we can consider it as a fully developed flow, laminar flow and incompressible, right? So assuming that you derive, find this, the power. I'll give you 2 minutes for this. Okay, let's go and solve this as well. So first of all, as it is fully developed, we can simply apply Hagen-Poiseuille's equation. So 32 mu u bar L upon d square. So this is 32 into 2.33 into 0.5 into 330 multiplied by 0.28 square. So this will come out to be 156.918 kilopascal. Now the volumetric flow rate can be found out as pi d squared by 4 u bar. So 3.1415 multiplied by 0.28 squared by 4 multiplied by 0.5. So this will come out to be 0.0307 meter cube per second. So now the pumping power we need to find. Pumping power will be nothing but the pressure multiplied by the volumetric flow rate. So this is 156 pressure drop multiplied by flow rate. So 156.918 0.0307. So this will be 4.83 kilowatt. Done. Now let's proceed to the next question. So this is a combined question where a Newtonian fluid is slowly flowing under gravity through an inclined plane, inclined flat surface that makes an angle theta with the horizontal. The film thickness is T and it is a constant. The flow is two-dimensional and nu is the kinematic viscosity of the fluid. So what is the velocity? We need to find the expression for velocity, the average velocity and the volumetric flow rate. So I think it's easy and you can do it. So you just need to do the balances. So I'll give you 3 to 4 minutes to solve this. Okay, all of three. I think we should proceed with the solution. So let's go on. So first of all, the flow is entirely gravity driven, and hence the pressure difference is zero, as both the inlet and outlet sections are open to atmosphere, right? So from Navier-Stokes equation, for a fully developed flow over an inclined plane, we get like if we cut out the other terms, we get d square u dy square plus rho g sine theta is equal to 0. So now integrating, if we integrate this, we'll get g sine theta mu y t minus y by 2. So that means option C. Now we need to find the average velocity for a width of b in the plane into the paper. The average velocity is given as u bar is equal to u dA upon a. So that means 0 to t u b dy bt. It is the thickness of that film. 0 to t g sine theta nu y t minus y by 2 dy upon t. So this u average will be is equal to g sine theta t square by 3 nu. So this is option B. Now the volumetric flow rate is given as 0 to t u dA upon no sorry, just a second. So this will be 0 to t g sine theta by nu y t minus y by 2 to 1 dy. So this will be g sine theta t cube 3 nu. So this is option C. Yeah. Okay. Now the next question. Okay. So water is at 20 degrees Celsius is flowing between two-dimensional channels in which the top and bottom walls are 1.5 millimeter apart. If the average velocity is 2 meter per second, find out the maximum velocity, pressure drop and the wall shearing stress. And you have to consider it from the base, like you have to like first take the continuity equation and for the fully developed flow it is said na the fully developed flow. So we'll, if it's not said, we'll assume fully developed flow. So fully developed flow, if it is there, then we will then formulate the velocity, like which velocities are important, like b u among this, and then we'll take the Navier-Stokes equations and we'll cancel the proper terms. We'll keep the proper terms, pressure or which velocities will be there, which differential equation, differential values will be there, and then we'll put the boundary equation and we'll formulate to find the velocity equation, the velocity profile equation. So after that we'll find the average velocity from there, and in terms of formula, right? And after that we'll find the shear, like wall shear stress and the skin friction coefficient. Then we can like use the like that formula to find out this, like to solve this problem. So you have to start from the basics. So it will take 5 minutes to solve this most probably. So you better start solving, and I'll be here only. Oh, I don't know whether you have seen the other solution, like the previous solution. I think I have not shared this screen. Okay. So the previous solution, like, is this one. See what I've told, I've same thing I'm showing here. Right. Okay. So solve this one. Okay. Let's start with the solution. So first of all, we have considered fully developed flow, right? So first of all, we'll start with continuity equation. So del u del x plus del v del y is equal to 0. So for fully developed flow, obviously del u del x is equal to 0. So that determines what? The del v del y is equal to 0. That means v is not a function of y. And v is equal to 0 at y is equal to minus h plus h. So v is equal to 0 for all y. Now we write the 2D Navier-Stokes equation in the y momentum equation, right? So rho del v del t plus u del v del x plus v del v del y is equal to minus del p del y plus mu del square v del x square plus del square v del y square. B is equal to 0 for all y. Therefore, if we write everything else, so from here we can get del p del y is equal to 0. That means p is a function of x only, right? So p is a function of x only. Now, if we will write 2D Navier-Stokes equation for like that is in x direction, that means x moment. So if we will write that, so let's write that up. So del u del t plus u del u del x plus v del u del y is equal to minus del p del x plus mu del square u del x square plus del square u del y square. So from here, del u del t is 0 for steady flow, and for fully developed flow del u del x is 0. So del u del x 0 and v is equal to 0. So this whole thing cancels out left hand side. For the right hand side, del u del x obviously del square u del x square will also be 0. So only these two comes into picture. That means del square u del y square is equal to del p. Just 1 second. That means del p del p del x. This is me. So now p is a function of x only, and u is a function of y only. That means dp, we can write this dp dx is equal to mu del square u dy square is equal to some constant c. Now p is a linear function of x and u is a quadratic function of y. Now if we will integrate, we will get du dy is equal to c by mu y plus c1, and u is equal to c by 2 mu y square plus c1 y plus c2. Now the boundary conditions, one will be y is equal to h, u is equal to 0. Now y is equal to minus h, u is equal to 0. Boundary condition 2 is du dy is equal to 0, y is equal to 0. So u max is at y is equal to 0. Now integrating, if we'll integrate this, then we'll get c1 is equal to 0 and c2 is equal to minus c square by 2. So u we will get as h square by 2 mu minus dp dx 1 minus y square by h square. Now this is a plain Poiseuille's flow, and average velocity is given as uda upon a is equal to, from minus h to h u dy b by 2h b to h. So this will c by 2 mu 0 to h y square minus h square dy upon h. So this will come out to be c by minus 3 mu h square. So c is equal to minus 3 mu u bar by h square is equal to dp by dx. This is equation 2, and which one is equation 1? This one is equation 1, right? Yeah. So in equation 1, if we will put the value of dp dx from equation 2, so we'll get u by u bar is equal to 3 by 2 1 minus y square by h square. Now u max at center line y is equal to 0 is equal to minus 1 by 2 mu dp dx h square. So u bar by u max is equal to 2 by 3. Shear stress at wall tau w is equal to tau xy wall. So is equal to mu du dy plus dv dx wall. So is equal to mu del u del y at y is equal to plus minus h. So this is equal to minus dp dx h by mu. This is using equation 1, right? So now using equation 2, tau w we can write as 3 mu u bar by h. Now okay, so we have found out everything. Now let's solve this question. So u max we need to find out, that is 3 by 2 u bar. So 3 by 2 into 2, that is 3 meter per second. Now for 2, like part 1, part 2, this is pressure drop. dp dx is equal to minus 2 mu u max by h square. So that is minus 2 into 0.00101 whole multiplied by 3 u max, that is 1.5 h square, 2 into 1000 whole square. So this will come out to be minus 10773.33 Newton per meter cube, that is Newton per meter square per meter. Now the next is wall shear stress. So wall shear stress will be mu du dy at wall. So this is minus h. Okay, just 1 second. Okay. So tau w is equal to mu du dy at wall. So this means minus h dp dx. So this is minus 1.5 to multiplied by 1000. And multiply dp dx we already have found out, so this will come out to be 8.080 Newton per meter square. Okay, so let's proceed to the next question now. So two viscous incompressible mixable fluid of same density are there but different viscosities, right? So viscosity of the lower fluid layer is mu1 and upper fluid is mu2, that is mu2 is less than mu1. Flow in separate layers between two parallel plates located at y is equal to plus minus h. As the thickness of each fluid layer is identical and their interface is flat, the flow is driven by constant favorable pressure gradient. Derive the expression for velocity profile in the fluid layers. Also make a sketch of the velocity profiles. Assume the flow to be steady and plates to be infinitely large width. So find it out, the velocity profiles. Tell me the what will be the velocity profile. So I'll give you 2 minutes to solve this. Okay. Let's proceed with the solution. So first of all, we'll start with the continuity equation as usual. So this question number 8. So continuity equation is del u del x plus del v del y under incompressible flow condition. So this is equal to 0. For fully developed flow, del u del x is equal to 0. So del v del y is equal to 0. So v is not a function of y. V is equal to 0 at all h. Now considering the x momentum equation, rho u del u del x plus v del y is equal to minus del p del x plus mu del square u del x square plus del square u del y square. So using the okay, so what will happen? Here, from here, we can get that del square u del y square is equal to 1 upon mu dp dx is equal to constant. right? The others won't be there. So this is function of y only, this is a function of x only. So we can write it as a constant c. So we can write it as d square u1 dy square plus, sorry, is equal to 1 upon mu1 dp dx. So integrating, we get d u1 dy is equal to 1 minus v1 dp dx y plus c1. So u1 is equal to 1 upon mu1 dp dx y square by 2 plus c1 y plus c2. Now where c1 and c2 are the constants of integration. So from 0 to h, this is like again d square u2 dy square is equal to 1 upon mu2 dp dx. Now integrating the above equation, also we get u2 is equal to 1 upon mu2 dp dx y square by 2 plus c3y plus c4. This is from 0 to h, y is equal to 0 to h, and this is from minus 0 to h, minus h to 0 for both of the parts. Now, the first part, like what are the boundary conditions now? So there are two equations, we need four boundary conditions. Y is equal to minus h u1 is equal to 0, y is equal to h u2 is equal to 0, y is equal to 0, u1 is equal to u2, y is equal to 0, mu1 du1 dy is equal to mu2 du2 dy. The continuity of shear stress from the boundary conditions at y is equal to minus h, u1 is equal to 0, at y is equal to h, u2 is equal to 0, we get what? C1, C2, C4, so C2, I'm just writing it down. C2, we get C1, H minus 1 upon mu1 dp dx h square by 2, and C4 we got minus C3H minus 1 upon mu2 dp dx h square by 2. Now from the boundary condition, the fourth boundary condition, that is this one, we have C1 is equal to mu2 upon mu1 C3. So from boundary condition u1 is equal to u2, third boundary condition, we get C2 is equal to C4. So one can write C2, C4 from here we can write. So both of them are equal. If both of them are equal, from there we can get the value of C3 and C1. So if you will solve this, I'll just write the final equations. So 1 by mu1 dp dx 1 upon 2 y square minus 8 square plus mu2 minus mu1 upon mu2 plus mu1 h y plus h. Now u2 is equal to 1 upon mu2 dp dx 1 by 2 y square minus 8 square plus mu2 minus mu1 by mu2 plus mu1 h y minus h. So these are the velocity profiles that we need. Let's proceed to the next question. We don't have much time, it's already 6, so we'll proceed fast. So this question number 9. Okay, so there are two infinite parallel plates, and at a h distance apart there is a fluid of viscosity mu between the plates, and the pressure is constant. The upper plate is moving at speed, so this is simply quiet flow. So the height of the channel is 1.8 centimeter, and calculate the shear stress. So we have done problems like this earlier, so I think it will be easier for you to solve. Right. This is very like 1 minute problem. So should we proceed? So okay, so what will happen? Uh, This Reynolds number will be rho hu by mu. So this is 888 1.8 upon 1000, sorry, 100 multiplied by 4. Sorry, this is 1. Okay, and this viscosity is 0.4. So this will come out to be 145, and the flow is laminar. So tau is equal to mu du dy, and u at any y is given as u by hy. So the shear stress at two walls are of equal magnitude. Therefore, tau is equal to mu del u del y is equal to mu u by 0 upon h. So this is equal to 0.44 multiplied by 4 upon 1.8 upon 100. So this will be 97.8 Pascal. Yes. So let's proceed to the next question. Okay. It was not visible or what? Just one second. I'll display you the solution again. This is the solution. Okay. So let's proceed to the next question. So what is said here that water at 60 Celsius flows between two large flat plates. The lower plate is moving at some velocity, like again plate flow. The plate spacing is 3 mm and the flow is laminar. Determine the pressure gradient required to produce zero net flow at a cross section. The viscosity is given. So we'll use Navier-Stokes equation at first only, and we'll cancel terms that is not required, and then from there we'll get the velocity profile. Velocity profile will apply the boundary conditions and get the actual velocity profile, removing the constants. From there we can get the like integrate the velocity to get the volumetric flow rate. So from the volumetric flow rate, like from the in the main equation, if we'll put, then we will get the pressure gradient. So I think we should solve because time is already up. So the governing equation is mu d, like the from the momentum equation we'll get this is equal to dp dx. So u is equal to half mu dp dx y square plus c1y plus c2. So from here at y is equal to 0, y is equal to 0, u is equal to minus u. So from there we get c2 is equal to minus u, and at y is equal to b, u is equal to 0. So that gives c1 is equal to u by b minus 1 by 2 mu dp dx b. So from here we get velocities is equal to 1 by 2 mu dp dx y square minus by plus u y by b minus 1. So from here we can get q is equal to integration 0 to b u dy. So from here if we'll integrate it, we'll simply get minus 1 upon 2 mu dp dx b cube minus ub by 2a. So volumetric flow rate, if we'll put 0 and viscosity is given, so dp dx will get minus 6 u mu by b square. So this will be minus 94 Newton per meter square meter. Okay, done. So I hope you have understood it. Let's proceed to the there are two more questions left then. So there is a fully regular flow and we need to derive the velocity profile. So that's it for this question. So let's solve this as well. Like take 30 seconds to even understand the question. Then we'll proceed with the solution. Okay, so let's solve this. So get on the other screen. Okay, so I think the writing pad is visible and I'm properly audible. So for this question, first of all, the fluid moves due to axial pressure gradient, right? In the pressure across the section, so the pressure can be regarded as constant. Due to the viscous friction, the individual layer act on each side, producing a shear stress which is proportional to del V Z del R. In order to establish the condition of equilibrium, we consider a fluid cylinder of length delta L and radius R, right? In this only we'll be considering just a cylinder of length delta L and radius will be R. Radius will be R. Just 1 second. Right? So now we can write P minus P plus dP pi R square is equal to minus tau 2 pi R delta L. So if we will solve this, we'll get d p dz r 1 by 2 mu is equal to del vz del r. So if we'll integrate this, vz is equal to 1 by 4 mu dp dz r square plus k. At small r is equal to capital R, vz is equal to 0. So k is equal to minus 1 by 4 mu dp dz r square. So vz is equal to r square by 4 mu minus dp dz 1 minus small r by small r square by capital R square. So this is it, the expression for vz. Let us proceed to the next and last question. So the velocity distribution for a fully developed laminar flow is given. The velocity profile is given, and we have to determine the radial distance from the pipe axis at which the velocity equals the average velocity. Just we'll get the velocity. We'll find the average velocity first. We'll find the formula for that. We'll equal both of them, and from there we'll find the radius. It's very simple. So let us solve this. So Vz is given, right? So Vz bar, that means the average velocity. We can simply find out volumetric flow rate upon area. So that means 1 upon pi r square, 0 to r minus r square by 4 mu del p del z 1 minus small r by capital R whole square 2 pi r dr. So this is equal to r square by 8 mu del p del z. So it said that Vz is equal to Vz bar. So if we'll make both of them equal, so we'll get 1 upon r by small r, rest of them will cancel out. So is equal to half. So small r by capital R whole square is equal to 1 by 2. So small r is equal to 0.707 capital R. So this is it for today. Okay, so this is the solution. Yeah, this is the solution. So from here it starts, question number 12. So Vz is equal to q by a 1 upon pi r square. So we have just find out this is the average velocity. Like, let me use some other color. This is the average velocity. So we have equated both average velocity and the velocity and the normal velocity profile, local velocity. So we found that this is what we are getting. So ours from there we can get, right. So it's pretty easy. So this is it for today's class. So I'll end today's class. Thank you for joining, and I'll meet you all in the last class that will be next week, most probably on Friday itself. So meet you there.